Hello, fourth grade, and welcome to lesson 2 of unit 2. For this lesson, we're going to talk about the transfer of energy by electricity. So think about any of the times that you've ever touched a door handle and received a shock. So think about it. Is there an electric current flowing? Is it flowing from you into the door handle, or is it flowing from the door handle into you? These are things we can think about while we're going through our lesson. Now, for our first pages, we're going to go ahead and complete page 52, where we're going to notice that these four friends all have different ideas about energy transfer and electric currents. So take a minute to read through this scenario and decide which one you agree with the most and explain why you agree with them. Once you finish that, we're going to go ahead and take a look at the photo of the light bulb. So I'm going to, of the flashlight. So I'm going to pull up that photo for you now. Take a minute to stop and think about this picture and write down any questions that you have. Once you've written down your questions, we can read about our STEM career connection, about the electronics engineer. So physicists and other scientists always ask questions and come up with experiments to learn how the world around them works. Engineers find solutions to specific real-world problems. So once you've completed reading this section, go ahead and answer the questions on the following page. Why do you think an electronics engineer must test a design many times? And what do you find interesting about the electronics engineer's career? Then go ahead and answer your essential question. How do electric currents transfer energy? So one thing an electronics engineer needs to understand is how energy is transferred through electric currents. How do you think those currents transfer energy? And then try and answer that essential question on your own. Once completed, we're going to hop over to our next set of pages, and we're going to have an inquiry activity called Simple Electricity. So we're going to investigate the very basics of electricity, and you're going to see the effect of using more than one battery to make a light bulb light up. Now make sure that when you're making your drawing that you try and make it as accurate as possible. Make sure you label it, all of the parts of your diagram, after, of course, you've written out your prediction. So your prediction here, you need to predict what effect will using more than one battery have on a light bulb. So after you've completed the investigation, what scientists and engineers do is they communicate to others the information that they gathered through their observations and through their experiments. This way they can learn from each other. After you've completed this, you're going to follow the directions all the way through, and then you're going to communicate the information. How did the results of adding a battery compare to your prediction? Explain, this part is really important. Explain your reasoning. Where is the energy coming from to make your device work? And what type of energy transfers have you observed in this activity? Now, after we've completed this, we're going to jump into our next page and we're going to talk about our vocabulary words. So the vocabulary words we're going to focus on are electric current, circuit, switch, resistor, electromagnet, and generator. So when you made your prediction about the effects of using more than one battery to light up the bulb, did you use any of your science words? So as we continue to discover more about electric currents, you're going to learn several words that'll help you explain transfers of electrical energy much more clearly. Let's take a look at our vocabulary words and go over their meanings together. Your first one is electric current. A flow of electricity through a conductor is an electric current. Now remember, a conductor, we learned about this one in our previous lesson, is a kind of material that allows electricity to flow through it easily, or even heat to flow through it easily. It conducts, or it allows it to go through. A circuit is a path through which electric currents can flow. So we're going to learn a lot more about electric currents as we go through our reading. And we're going to learn more about circuits as well. So think about a piece of wire that's looped all the way around like a circle or an oval. Electricity can pass through it freely, can keep looping and looping and looping around, traveling around that circuit. A switch is a device that can either open or it can close a circuit. Now think about a light switch when you turn it on. What happens to that circuit? What happens when you turn the light switch off? What we're going to learn is that when you open a circuit, you are actually stopping the flow of electricity. And when you close the circuit, you're reconnecting it and you're allowing electricity to flow through. Next, we have the word resistor. A resistor is an object in an electrical circuit that resists the flow of energy. So it's something that does exactly what it sounds like. It resists or it tries to stop the flow of energy or limit the flow of energy. We're also going to talk about electromagnets. An electromagnet is a magnet that's formed when an electric current flows through a wire that's wrapped in coils around an iron. So think of like an iron nail with a wire wrapped all the way around it. Now, as the electric current flows through that wire, that iron nail becomes a magnet. And last, we have the word generator. A generator is a device that produces alternating currents by spinning an electric coil between the poles of magnets. It changes motion into electrical energy. So we're going to go ahead and read a lot more in our science handbook before we go on to the questions. We're also going to watch a short video called The Uses of Electricity on how people use electricity every day. Then we're going to answer the questions. List what electricity is used to produce and in what ways do you use electricity every single day?
Electricity is all around us and is something that many people use and enjoy every day. Electricity is the result of electrical charges. You cannot see, smell, or weigh an electrical charge. It is a property of matter, like color and hardness. Electricity is used to produce light, heat, sound, and motion. There are many ways to produce electricity. The strong water flow from a river or dam can create electricity. The water is sent through a turbine, causing it to spin, which creates energy. This is called water power. Wind spins windmills to produce energy. This is called wind power. Another way we produce electricity is with solar power. Solar power uses a tool called a solar cell that collects energy from sunlight. Electricity is used to produce many of the things we use and see every day. What do you use each day that uses electricity?
All right, now that we've finished watching that short video, you can go ahead and answer the questions. List what electricity is used to produce, and then in what ways do you use electricity every day? Once you've completed that using complete sentences, we're going to go on to reading page 314 and 315 in our science handbook. And we're going to answer the following questions. Number 3, how is the flow of electric current similar to the flow of water in a hose? Number 4, what happens to energy in a resistor? And then for number 5, we're going to go through the digital interactive electric currents in a circuit on how energy flows in a circuit. And then we're going to answer the bottom where we're going to write the function or the job of each part of these. So the job of the power source, the job of the switch, the job of the electric current, and of the fan. Let's go ahead and jump into our textbook. We're going to look at pages 314 and 315, and we're going to read about electric currents. When you're in the dark, a flashlight is useful. A flow of electric charge lights the bulb. Electric current is the flow of electric charge through a conductor. A circuit is formed when an electric current passes through an unbroken path of conductors. Often, the path of a circuit consists of wires. Circuits must also have a device to move electrons along the path. These devices, called voltage sources, increase the volts of electrons flowing in the circuit. Batteries are a voltage source. Different sized batteries produce different quantities of voltage or amounts of energy that move through a circuit. A switch is a device that can open or close the path of a circuit. When the switch is closed, the electric current can flow around and around through the circuit. When the switch is open, the current cannot flow. Electricity does not flow in the same way through every part of a circuit. An object in an electrical circuit that resists the flow of electrons is called a resistor. Electrons lose energy when moving through a resistor. The energy is transformed into a different form of energy, such as light or heat. A light bulb is a resistor. Resistance is measured in units called ohms. The chemicals inside a battery use a buildup of extra electrons. So let's go back and review what we just read. We know that an electric current is the flow of an electrical charge through a conductor. So it's constantly passing through it. A circuit is formed when we have an electric current that flows through an unbroken path of conductors, right? That means there's nothing in the way, there's nothing stopping it. It's just continuing to flow on and on. A switch can either open the path, which means it disconnects it, or it closes the path where it reconnects it. And that will either stop the flow of electricity or it will allow it to continue. Now we know that in order for electricity to flow, there has to be some kind of voltage source. There has to be some kind of power source. In this case, we're talking about batteries and a light bulb. So that battery, depending on the size of the battery, will produce different quantities of voltage or the amount of energy that will be released. So larger batteries will usually have a higher voltage than smaller batteries. Electric charge travels fast in a circuit, almost as fast as the speed of light, and much more electric charge moves as electric current in a circuit than the static discharge when a doorknob shocks your finger. The amount of electric charge moving in a circuit can be very powerful and very dangerous. Electric current is measured in units called amperes or amps. There are about 6 quintillion electrons moving every second in 1 amp of current. Even currents as small as 0.05 amps can seriously harm you. Your home has a collection of connected electric circuits hidden in the walls. When you plug in a device that uses electricity into a wall outlet, you're making the device part of a circuit. The wires and outlets are covered with plastic insulators to keep you from coming in contact with the electric current. So let's take a look at the pictures that we have here. At the bottom, we have our flashlight as part of the circuit. The batteries supply the voltage and the bulb acts as a resistor. So here's your batteries over here. Here we can see the wire that's connecting it. So it's taking that energy, it's flowing into the little light bulb part. And the light bulb functions as a resistor where it actually changes the kind of energy from electricity into light and heat. Now for the picture of the toaster, it says the wires to devices in a home are plugged into the home's electrical circuit. So when you're plugging it in, you're making that device part of the circuit, so it's receiving electricity through it. Electric charge flows in a wire in a way similar to water flowing through a hose. So think about the electric wires, and we talked about this in class as well, where that rubber coating on the outside of the wires is an insulator. It's something that keeps electricity or heat or whatever it is that's trying to pass through. It tries to keep it from passing through. It tries to block it. And we have that on electrical wires to keep us safe so that electricity is not flowing into us. Now we read over here in the passage that even a very small amount, a current as small as 0.05 amps, can still cause serious harm to a person. So as we can see, the electrons are flowing from the battery, this is our energy source, through the wire, and it flows similar to a garden hose. So that energy, that electricity, those electrons are being pushed through that wire the same way water gets pushed through a garden hose. So go ahead and head back over here, answer your questions. How is a flow of electric current similar to the flow of water in a hose? What happens to energy in a resistor? And then after you've completed those using complete sentences, we're going to move on to our digital interactive activity, and we're going to look at electric currents in a circuit and talk about the different parts. All right, let's go back and take a look at our electric circuit. Whoops.
Click on the pop tips to learn about the circuit. Circuit illustration. Circuit illustration. Electric current. The electric energy will flow along the lines in this circuit. In an actual circuit, the lines would likely be wires. Trace the line with your finger to each of the connected devices. Power source. This provides a source of energy for the circuit. In this illustration, electric energy will move counterclockwise.
All right, so let's stop for a minute and look at what we just read. So your power source will usually be your battery. And if we look down here at the key, we can see that the plus and minus, just like you would have a plus and minus side on a battery, is your cell. Then we're going to go over here to the switch. And that's what looks over here like two circles with the line running across the top. We're going to read about what a switch does.
Switch. When the switch is closed, electric energy will flow through the circuit. When the switch is open, electric energy will not flow. The switch is closed in this illustration.
All right, so take a look over here. The switch is closed. You can see that it's still connecting both sides over here of our circuit. So energy and electrons are going to flow from the cell through the switch, and then we're going to follow it along as we go. So the electric energy will continue to flow along the lines of the circuit, and the electric energy will move towards the switch. As electric energy flows through the light glows. Electric energy transfers some energy to the light energy, some energy to light energy and to heat energy. The remaining energy continues to move along the circuit. So think about anytime you've turned on a light bulb. If you stand close to it or you put your hand near it, you can feel heat coming off of it as well as seeing the light. So if we have energy flowing through this, it's going to turn on the light bulb. An electric energy flow through the buzzer. The buzzer makes a sound. Electric energy transfers some energy into sound energy, and the remaining continues to move along the circuit. So some of the energy is going to go to powering that light bulb. Some of it is going to go into that buzzer to make the sound turn on. And then we're going to have some that goes towards the fan in this particular circuit. So a fan is connected to the circuit. As electric energy flows through the fan blades will start to spin. Electric energy transfers some energy to kinetic energy and a small amount of heat energy. The remaining energy continues to move along the circuit. So as energy is flowing through these, it's going to continue to power these different devices. So your power source here is going to continue to provide electrons flowing around and around until it runs out. The switch, so long as it's closed, will continue making all of these things work. But as soon as that switch is opened, that's when energy is going to stop flowing through these different things. So we're going to go back over here. We're going to go and list the function or the job of the power source. Now, if you don't remember, you can always go back. So our cell over here was our power source. It provides a source of energy for the circuit. For our next part, the switch. Our switch will either allow the flow of electricity or it will block the flow of electricity. So when the switch is open, electricity or electric energy cannot flow. When the switch is closed, electric energy can flow through it. Next, we have the electric current. The electric energy will flow along the lines in the circuit. In an actual circuit, the lines would be like wires, would likely be wires. So the electric current will be the energy that's flowing through the circuit. Next, we have the fan. Over here, we can see in our fan, what happened was when electric energy flows into the fan blades will start to spin. Electric energy transfers some of that energy into kinetic energy to make those fan blades swim, and a small amount or spin, and a small amount of it will be transferred or transformed into heat energy. So if you've had a fan on for a really long time and you put your hand near where the motor usually would be around the back of the fan, you can feel some residual heat coming off of it. Now, once we've completed page 58, we're going to go on and we're going to take a look at page 60. Oops. Oh, sorry, we had already gotten here. Now, on page 60, we're going to explore the digital interactive energy sequence on how electricity travels from a source to your home. And then we're going to answer the question. Explain how electric energy moves from its source to the point at which it can be used. So how does energy go from where they start collecting it to where it's usable energy for you? Okay, so coal is mined from under the Earth's surface. Most of the coal that's mined is used to produce electricity. Coal trucks transport the mined coal to a coal power plant. Next, electricity is generated at the coal power plant. Here, the coal is burned to heat water and create steam. The steam is used to spin a turbine. It's this spinning turbine that generates the electricity. Then the electricity travels from the power plant to these transformers that you're seeing over here in the photo. The transformers increase the voltage. The voltage is an electrical force that moves electricity from place to place. Having a higher voltage allows the energy to travel through the power lines over long distances more effectively. These high voltage lines transfer electricity from power plants into different towns. So remember, they mine the coal, they take it to the coal plant, it's transformed into electric energy. That electricity then goes from the power plant into these transformers, these giant wires that you'll see a lot of times. And then the voltage is increased while it's passing through these transformers and moves into places like towns and cities. When the electricity nears your town, the voltage is too high to be used and the voltage must be lowered so that the electricity can be used in your home. The high voltage electricity first goes to a substation where the voltage is lowered, and then the lower voltage electricity can be sent onto smaller power lines, which are the ones you're used to seeing near neighborhoods. So those small power lines distribute the electricity to your neighborhood. Some of the poles that support the power lines also have small transformers on them. These transformers further reduce the voltage to make sure the electricity is safe to use in your home. So when it's first coming out of the power plant and those transformers increase the voltage, it's to get the electricity to travel faster and more effectively. But once it gets close to a town or a neighborhood, the voltage is too high and they need to lower it so that it's safe to use in your home. The power lines connect your home through an electric meter. This meter keeps track of the amount of electricity that your family uses. So think about, you can ask your parents about this, that the amount of electricity you use in the summertime may be greater than what you would use in the springtime. For example, if you have air conditioning and you're turning that air conditioning on in the summertime, or if you're turning the heater on frequently in the wintertime. So these meters keep track of the amount of electricity you're using. They connect the power lines to your home, and it basically keeps track of the amount that's being used. The meter on the outside of your home is connected to a service panel located indoors. Wires are connected to the service panel and carry electricity to the electrical outlets and switches in your home. Don't ever touch a service panel. Only a parent or professional should operate the service panel in your home. You can ask your parents to see what it looks like. They look very similar to the picture here. They have a whole bunch of switches on them, but again, make sure you're not touching anything yourself. Now, when you plug in an electronic device or flip a switch to turn on the light, electricity flows to the device or to the light. It's pretty amazing to think about how the journey that electricity made that you use every day travels all the way from coals and power plants, so it's usable in your home. Now, we're going to answer this question: explain how electric energy moves from its source to the point at which it can be used. And you can go back and take a look at the slides one more time so that you're able to answer that question. All right, next we're going to take a look at page 61. And for page 61, we need to read pages 324 to 327 in our science handbook in order to answer these questions. The two questions we need to answer are to have a working electromagnet, what has to happen? And number two, what is the difference between a motor and a generator? So think about, have you ever seen a motion sensor light? Is it a light that will turn on when a device on the wall senses motion in the room? Did you know that a special kind of magnet called an electromagnet is used to make that device work correctly? We're going to go ahead and read in our handbook to learn more about how electromagnets produce electricity and how they're used in many electrical devices. Electromagnets. Electricity and magnetism are related. When charged particles move, they form magnetic fields, which means they can use electric current to make magnets. An electromagnet is an electric circuit that produces a magnetic field. The effect of a current. The simplest electromagnet is a straight wire. The magnetic field circles the wire when the current is flowing through the wire. The more current, the stronger the magnetic field. Turn the current off and the field disappears. The effect of coils. When you wrap a wire into a loop, you increase the strength of the magnetic field. Many loops together can make a coil. The magnetism from each loop adds up to make the coil a stronger electromagnet. The coil's magnetic field is shaped like a bar magnet. So let's take a look at what we read. So far, the simplest electromagnet is just a straight wire. Now, if you're wrapping a wire around it and making a coil around the wire or the nail or whatever it is that you're using, every time you're making that loop with the wire, you're strengthening that magnetic field. You're increasing it, making it stronger and stronger. So this is what it would be like with a straight wire. You see a little bit of a magnetic field forming around it. Now, when you put any kind of loop, you're increasing that electric field. And now we're going to read about the effect of an iron core. Placing a rod of iron inside the coil of an electromagnet will magnetize the iron. So that means that core, that iron core, whether it's a nail or just a piece of iron, will also become magnetized, or it will become a magnet once you place it inside of those coils. The rod of iron adds to the strength of the electromagnet's magnetic field, and that's because iron is a conductor. So electrons moving in a wire produce a magnetic field. A loop of electric current will have north and south magnetic poles, just like a regular magnet. The magnetic fields of a coil is like that of a bar magnet. Using electromagnets. Electromagnets must be part of an electric circuit in order to work. Because circuits usually include a switch, an electromagnet can be turned on and off. The ability to turn the magnetic field on and off makes electromagnets useful in many devices. So think about a circuit. If that switch is open, there's no flow of electrons. There's no flow of electricity. So that electromagnet stops being a magnet when the flow of energy stops. And it continues to be a magnet, or it returns to being a magnet when that switch is closed. Audio speakers. A voice coil is an electromagnet in an audio speaker. The voice coil sits on the magnetic field of a nearby permanent magnet. Electric currents in the voice coil can change. That changes the coil's magnetic field. The coil's changing magnetic force interacts with the magnetic field of the permanent magnet. Pushes and pulls between the two magnets make the coil magnet move back and forth. The coil is connected to a cone of paper or metal. The coil's vibrations make the cone move back and forth to produce sound waves in the air. So take a look at the bottom where we see a picture of this speaker that looks like it's been cut open. So we have the voice coil right there in the center. We have the magnet that it sits on at the bottom and this spring that goes around it. Now we can see over here, we've got the coil that's wrapping around. A voice coil vibrates next to a permanent magnet to produce sound. So over here, this cone or the top or outside of the speaker that you usually see is the part that will vibrate when sound waves are produced. Electric motors. A simple electric motor has three parts. It has a power source, a magnet, and a wire loop attached to a shaft. The shaft is a rod that can spin. The power source produces electric currents. The current runs through the wire loop, making it into an electromagnet. The magnet pushes and pulls on this electromagnet. The force then causes the loop and shaft to spin. The spinning shaft usually attaches to a wheel or a gear that's used to do work. Let's take a look at the illustration that we have here. We have our magnet with the north and south sides. We have the loop of wire over here. And we have our energy source, which in this case is a battery. Now let's go ahead and finish up these questions. Have a working electromagnet. What has to happen? So go back to the text. Take a look at the section. The section on electromagnets and what you need to go ahead and answer that question. What is the difference between a motor and a generator? So follow directions in the arrows to understand what happens to the shaft of the motor when the loop of wire that surrounds it spins. So this has a motor. We can look at the difference between electric motors and our definition back when we were talking about our vocabulary about what a generator is and list how those two things are different. Make sure you're using complete sentences and indicating or telling which one you're talking about as you describe it. After you've completed that, we're going to watch how a generator works, and we're going to answer these questions after we finish. So number 3, describe the energy transfer that takes place in an electric generator. What causes this transfer to happen? All right, let's head over to that section. And we're going to find out how a generator works.
This generator uses wind to make electrical energy. Electrical generators turn mechanical energy into electrical energy. A turbine provides the mechanical energy for the generator. A simple turbine has blades like a fan. Steam, water, or air is used to turn the blades. Wind moves the blades of this turbine. The blades are attached to a shaft that spins a wire loop or magnet inside the generator. In this generator, the shaft is connected to the wire loop. A magnetic field exists between the north and south poles of the permanent magnet. As the wire loop turns in the magnetic field, electrical charges are pushed through the wire. An electrical current flows through the wire. The electricity goes through power lines to reach places such as your home. Electrical generators produce nearly all of our electrical energy.
All right, now think of a fan or picture a fan. What parts of the fan move the air around? Now we know that the fan blades are the part that move the air around. So why are the blades important in a turbine the same way they are in fans? And think about, how does the turbine provide mechanical energy for the generator? So think about the way a turbine works, about how those different parts flow, and what kind of energy is produced when those fan blades or the giant turbine blades are moving around. How is that used to convert that wind energy into electrical energy? Once you're done, you can go ahead and answer the question at the bottom of page 61. Describe the energy transfer that takes place in an electric generator. What causes this transfer to happen? Now for pages 62, we're going to think back about the question we wrote about the flashlight at the very, very beginning of our lesson. Now that we learned a whole lot more about energy transfers, there's a good chance you can answer most of those questions now. As an electronics engineer, you're going to carry out another investigation. So you're going to write your hypothesis. Does the position of the batteries in the flashlight have an effect on how the flashlight works? So think about where the batteries are and how they're placed, and if that has any effect on how well your flashlight is going to work. So carefully take apart the flashlight and observe each part to determine or figure out its function. Draw a diagram in the box and label each part and the function of that part. So you're going to draw, you're going to label, and you're going to explain what each part does. After you've done that neatly and carefully, you're going to put your flashlight back together and make sure the batteries are both facing the same direction. The raised end of each battery should be pointed towards where the light bulb will be located. And then you're going to turn the flashlight on. After you do that, you're going to take the batteries out and replace them so that the batteries are backwards. So the raised end of the battery should now be facing away from the light bulb. Put it back together and turn it on. Then take the batteries out, replace them so the raised ends are touching each other. Put it back together and then try and turn it on. And then describe what happens in each one of those different arrangements of batteries. Write your observations in the boxes. Please remember to write neatly. Then underneath, we're going to communicate the information that we found. Use the evidence that you gathered to create a diagram that shows how the working flashlight is an example of an electrical circuit. Label the flow of the electric current in your diagram. Next, describe the energy transfer that occurs within the battery that allows the light bulb to give off light. How is energy transferred by electric current? Use your diagram and the evidence that you collected to help with your explanation, and then give evidence that the electric currents transfer energy from place to place through your home. Give an example of how electrical currents are used to produce motion, sound, heat, and light. So you need an example of each one of those things. Once you've completed that, we're going to go on to the last page, and we're going to think about our essential question. Think about the photo of the flashlight at the beginning of the lesson Explain how electric currents transfer energy in electric circuits like the flashlight you observed. Once you've done that, you'll be all done with this lesson. If you have any questions, definitely let me know. Otherwise, I hope you guys have an amazing day, fourth grade. Take care. Bye-bye.